All right. These notes are going to be over the HR diagram. So the HR diagram is a short name for Hertzsprung-Russell diagram, and the HR diagram plots each star on a graph and measures the star's magnitude, so luminosity or brightness, against its temperature or spectral class or color. So on the up and down, that is magnitude or brightness, how bright it is and how big it is. And then on the bottom, it is the temperature. And it also determines the color. So the temperature determines the color. Right? So luminosity, brightness, or magnitude, they are all the same thing. It is the amount of energy or light a star emits. So how powerful or bright it is. And that is how we say how bright a star is. And typically the bigger the star, the brighter it is because it's emitting more light that we can see. So temperature, which is on the bottom, it is measured in Kelvin. So 237 Kelvin is about 32 degrees Fahrenheit. The color of the star relates to its temperature. So if we look at the HR diagram on the right, so this one, how does the temperature change as you move from left to right? So if I'm moving from left to right, if you look at the temperature right here, it is decreasing. So typically when we look at graphs and stuff in math, as you move further right, it increases. Well, the HR diagram, it decreases. So the cooler stars are on this side and the hotter stars are on this side. And the color of the stars that are the coolest are the red, and the hottest are the blue. So it's opposite of what we see hot and cold as far as color-wise, and that's just something you have to remember. The hottest on the HR diagram is always going to be blue, and the coolest is always going to be red. So spectral class. The spectral class relates to the elements the stars absorb in their temperatures. So spectral class will also be on the bottom because it has to do with the color and temperatures. So it's O, B, A, F, G, K, and M. So every single time we ask you a question, these will be labeled for you. And it kind of just breaks it up. So if something is in spectral class K, it's going to be right here, the orangey color. If it's M, it's going to be more red. And if it's O, it's going to be blue. The main sequence is these stars right here, this group of stars. It includes about 90% of the stars in the universe, including our sun. So our sun would be like right here because it's yellow. And all of these stars are middle-aged. So that means they're not baby stars, but they're not old stars. And it's this entire range right here. That's why there's so many. That's why 90% are included right here because it's such a big chunk of the graph. Now our sun, as I said, is in this area. It is an average sized star with average brightness and average temperature. And so average kind of just means middle. So that's why it's in the middle of the luminosity and close to the middle of temperature. The temperature is about 5,770 Kelvin. It's in the color yellow and spectral class G. G's are your yellow ones, and those go up and down. Red giants, they're right above the main sequence. They are a dying star. So our own sun will turn into a red giant, expanding to engulf the inner planets. So no need to freak out now. This is going to happen in millions and millions of years. But eventually our sun will grow and become a red giant as it starts to die. Supergiants are on the very top because remember this is how big and bright they are. So the higher we go to the top, the bigger they are. So they are the largest stars in the universe by size. They take up most space, but do not have the biggest mass. So they're very huge, but they're very light because they're made up mostly of gases and different elements and stuff. And then white dwarfs, they're right here. They're literally white and they're dwarfs because they're so small. They are a very dense star that is typically the size of a planet, and they are formed when a low mass star has lost all of its fuel. So these ones aren't going to be as bright. That's why they're at the bottom right here, but they're very hot. That's why they are in this corner. They are basically already dead. They're dead stars. That's because they don't have any fuel left, so they don't have the pretty colors that are burning with them. And just like we saw in the lab, they don't have anything left in them. All right, so which section of the diagram includes the coolest, brightest stars? So that would be 2. They're coolest because they're on this side, but they're also the brightest because they're on the top. What section of the diagram includes the hottest, dimmest stars? That would be 3. That would be where your white dwarfs are. They're really hot, but they're not that bright. So they're really hot, so they're on this side. And they're not bright, so they're on the bottom. All right. Based on the information given, which of the following stars is most likely our sun? So remember, our sun is kind of right here. It's in the yellow part of the HR diagram. It's average, so it'll fall in right here, and that is 3. And then the star Polaris has a temperature of 6,000 Kelvin. Which spectral class would Polaris be in? So 6,000 is right here. We go down and ask for spectral class, so it is spectral class F. All right, I hope this helped.